The idea for this video is simple. If something's bigger than infinity, it's infinity. If something is smaller and positive, if something is smaller than something that's finite, it's finite. Okay. Now, if something's bigger than something that's finite, that doesn't tell us anything. If something's smaller than infinity, that doesn't tell us anything. But if it's bigger than infinity or smaller than finite, that's it. So that's essentially what this comparison theorem is. Okay? If f of x is less than or equal to g of x for all x in the interval from a to b, this is shorthand that means for all, an upside down capital A basically, and integral of g of x dx converges. Oh, let's say if let's say they're both positive too. They don't need to be positive. There's ways to split this up for negative situations. Let's worry about just positive. So if f is always smaller, well then the integral from a to b, and again b, we can let b be infinity here, even though that's not a real number. Right? Then the area under the curve of f is less than the area under the curve of g, if f is always less than g. So if the bigger one converges, then the smaller one converges. Similarly, if the smaller one diverges, then the bigger one diverges. Okay? Bigger than infinity is infinity. Smaller than finite, finite. That's what we're going to be using in this section. It's also very, very related to something that's done in Calc 3 when we look at sequences and series. So if you're planning on taking Calc 3, you're going to be seeing something like this again a lot. Okay, but I'm sure that's wonderful, and I'm sure you're all excited about that. Example 7. State, don't have to calculate it, whether these converge or diverge. Part A, integral from 1 to infinity of 1 over x e to the x dx. I don't know if we can evaluate this with the topics of this class. I want to say we cannot, but maybe if we were very creative, we could. Either way, it'd be a pretty messy integral, even if we could do it. But we don't have to evaluate this integral. We just need to know, does it converge or does it diverge? So we need to compare it with something. And before we even choose what to compare it with, we should kind of know and get an expectation for what's going to happen. Now, if you want to, you could rewrite this as 1 over x times e to the negative x. Now, e to the negative x goes off to 0 really, really fast. And in fact, it's pretty easy to show that this part converges. If we didn't have this, it'd be pretty easy to show it converges. This 1 over x part makes it annoying. But notice that the 1 over x part doesn't make it any bigger. In fact, it makes it smaller. So it's smaller, we think, our gut says it's smaller than something that converges. Okay? So let's make that comment. Right? If x is at least 1, then what happens if we divide something by x? If we divide by something that's at least 1, that's smaller or equal when x is 1 to just this. So we can set this up with the comparison theorem. So this is smaller, right? This is our smaller function. If you want, you could call this f and this g. If the integral of g converges, they're both positive. Something smaller that's positive, then something that converges must converge. Okay, so let's look at the integral from 1 to infinity of e to the negative x dx. We can do that pretty quickly. That's the limit as b goes to infinity of the integral from 1 to b. The antiderivative is negative e to the negative x. We can factor the negative out in front. So that'll be negative limit as b goes to infinity of e to the negative b minus e to the negative 1. This limit goes to 0. As b goes to infinity, e to the negative b goes to 0. This converges. Doesn't even matter what it equals. We just showed that it converged. It equals 1 over e. So, all right, if the integral of g converges and g is bigger, f also converges. The integral from 1 to infinity of 1 over x, e to the x dx, converges by the comparison theorem. That's our proof. It's a logical ordering of steps, right? This whole thing is the answer. All right, well, actually it just said state whether, so I guess this is the answer. But if it said state and show your work or prove blah, 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 then that would work. All right. Let me know if you have any questions. We'll do another one. The integral from 1 to infinity of 1 over x to the p dx, p is less than 1. And again, before I go any further, I do want to just graphically look at this last problem that we just did. Right, 1 over x e to the x. We're looking at the area under this curve from 1 to infinity. To the right of, to the right of this area under the curve. We said it converged. We said it's smaller than 1 over e to the x. Now notice that that's only smaller than this orange guy. Here, let me show you what their colors are. Oops. Right? It's only smaller than the orange guy when x is at least 1. So the area under this orange guy from 1 and to the right of 1 should be bigger than the area of the blue guy. We found the area of the orange guy was 1 over e. It was finite. The blue area is smaller than something finite. So the blue area has to also be finite. That blue integral converges. That's really what we're doing there. Okay. All right. Now this one, if p is less than 1, that means p can be negative. Means p can be a fraction. So what's the deal? Let's look at what's happening here. All right. So, does it really, hold on, does the example really not tell us whether it's positive or negative? I think it doesn't. But we can split this up by cases if we really, really want to. Oh, interesting. Okay. Let's just look at some examples and try to figure out what's going on. Right? If p is equal to like a half, we have 1 over the square root of x. If p is equal to 0, well, that's not very interesting. We just have the constant function 1. If p is negative 1, we have the function x. Do we have to worry about a natural log anywhere? No, because p can't equal 1. Okay. But now the question is, can we compare this to something and do we think it's going to converge or diverge? Well, in this case, it should definitely diverge, right? The area under the curve of x from 1 to infinity, this area, that should definitely diverge. So we're expecting that this, if there's a single answer for all of these p, we're expecting it has to diverge. So can we compare this with something? Is this bigger than something that we know diverges? And we may or may not have shown it, actually. I may not have included it. But the integral from 1 to infinity of 1 over x dx does diverge. So can we compare it to that? Do all of these compare with 1 over x in the same way? Noting that x is at least 1. Let's go off to the side and say, okay, if x is at least 1, then what happens between all of these? What happens to 1 over x to the p in comparison with 1 over x? P is less than 1. Hold on, there's got to be a smart way of setting this up instead of just stating it and checking whether it's true for some p. All right? There's got to be a good way of looking at it. Instead of, all right, so here's a smart way of approaching it, I think. We want, right, 1 over x to the p to be bigger than 1 over x, because we know this diverges, so if it's bigger than something that diverges, we're good to go. But that's kind of hard to show. But notice this is true if x to the p is smaller than x, right? If the denominator is smaller, the whole fraction's bigger. Now, is this true? This is easier to work with. All right, well, again, this is for x at least 1. Well, we can subtract x from both sides. That's true. Let's see. We don't know that this is true. We're going to have to go backwards at the end. Let's see. If this is true, that's equivalent. We could factor out an x to the p minus 1. Minus 1. So we know this is positive. Question is, what do we know about this? Well, if p is less than 1, then p minus 1 is less than 0. So p minus 1 is negative. So x to a negative exponent is going to be less than 1. Right? X to a negative exponent is less than 1. But you can't start with what you want to prove. You have to make sure it's reversible. So here's how we organize this. Start with this guy. If p is less than 1, p minus 1 is negative. That means some number bigger than 1 to a negative exponent is its reciprocal. Okay. Dividing by some number that's bigger than 1 is going to be less than 1. Okay. So that means that x times x to the p minus 1 is less than 0. Because again, this is positive, and that's negative. So when we distribute, x to the p minus x is negative, which means x to the p is less than x. Oh, these should all be greater than or equal to signs. All right, which means that 1 over x to the p is greater than or equal to 1 over x. Right, so this tells us this is useful, but it's not a proof. You can't prove by starting what you want. You have to start a proof by starting with what you know. Okay, it's an easy trap to fall into. This is useful work, but this is not part of our proof. This is what proves that we're bigger. All right, then, if that's the case, we can say if the integral from 1 to infinity of 1 over x dx diverges, then the integral from 1 to infinity of 1 over x to the p dx diverges. Again, p is less than 1. So you could go off to the side and do this, right? This is the limit. B goes to infinity. Integral from 1 to b of 1 over x dx. This should be quick. Limit as b goes to infinity. Its antiderivative is ln absolute x. And as b goes to infinity, this is the natural log of b. It's a positive number. Minus the natural log of 1, which is 0. Yep, that's infinity. Natural log of an infinitely big number is infinity. So, integral from 1 to infinity of 1 over x to the p dx diverges. Let's look at that. Okay. Integral from 1 to infinity of 1 over x to the p dx. So, if p is bigger than 1, this integral converges. If p is less than 1, integral diverges. We could visualize this as well. 1 over x to the p looks like this. And again, for negatives, we got weird stuff going on, but that's fine. It's going to diverge in any case. And if p is bigger than 1, this is the switching point. This integral from 1 to infinity diverges. This integral converges. Diverges, converges. Diverges, converges. Very similar though, but all of these are converging. Which we didn't prove the second half of that, but it's true. You do another convergence theorem, but not with 1 over x. So maybe you wouldn't do another comparison theorem. Well, you could do a comparison theorem for some of them, but not all of them. You could do actually all of them by hand and calculate them directly. But anyway, this one, you can't really calculate this one directly because there's too many cases depending on what p is. But if p is bigger than 1, then you actually can evaluate it exactly. Anyway, that's neither here nor there. Let me know if you have any questions, and good luck.